All right then. I think we'll get started. Hi everybody. Welcome to the session. Thanks for sticking around on a Thursday afternoon. I think we've got a pretty good session for you guys. We've got 5 speakers. We're going to start off with Dane Wright, who's going to be talking generally about what it is we do on the transformation train, what that even means. We're going to talk a little bit about Harmony with Dr. James Norton. Is it not on? Oh, okay. Is that better? Fantastic. All right. Hopefully people heard most of that. But yeah, we're going to start off with Dane Wright, who's going to talk about what the transformation train is, what it is we even do, what does it mean. We're going to move on to Harmony with James Norton. Then Danny Kaufman is going to be presenting on the Samba service chain, which is part of Harmony. I'm going to be talking a little bit about work we've done with some open source tools, and then Kit's going to follow things up with Aegis. So yeah, I think I will sort of hand things off to Dane to kick off.
Awesome. Thank you very much, Owen. So for those in the room and online, we do have a shared collaborative notes document here. You can get to it on the Sketch. I think it's Sketch. It depends on which way you say schedule, I guess. But anyway, the links here, collaborative notes. You're welcome to put your name and affiliation in there, and then you can take notes as we're going along. As Owen said, I'm going to give you a little bit of background on what the Transformation Train is and what we do. To tell you who I am the Transformation Train product manager. You've met Owen in the room there. He is the Transformation Train architect. We have another part of the triad who's at the top of the train. Heather Grahams is our release train engineer. Might talk about her in a minute. Talk about in general stuff here in a minute. All right. So first of all, what are transformation services, right? Probably most of us in the room have a pretty good idea of what these are. But I just wanted to make sure that we're sort of on the same page of what these services can be. And so they're data processing software, usually modular and that kind of thing, that takes data granules in some sort of raw format and processes them in some way to better suit the end user needs. So you can see the examples here with subsetting and aggregation, reformatting, and reprojection. All right, so why do we need these services, right? So the idea is that we're creating services to reduce time to science and make data more accessible. You know, scientists want to do science. They don't want to spend all their time doing data processing. That's kind of a thing that's come up, several times at ESIP. And it comes up all the time that, hey, we want to reduce the time to science so that we can get this work done faster. And we want to reduce those technical barriers to make data access more equitable to everyone. Large data sets are getting larger, and downloading them is unreasonable. It's impossible. So we're getting to the point where we need to give smaller amounts of data chunks, subsets, if you will, of data sets. We also want to compare data across different data sets. Interdisciplinary or multi-sensor science is really something that's certainly been around for quite a while now, but it's really a good way of finding information and answering questions that we all want to answer. And also these transformation services reduce the cost of data. I talked about how data sets are larger and that sort of thing, but larger data sets cost more to download out of the cloud. So if we can create ways of downloading smaller amounts of data, then that actually saves us money as NASA and us as the U.S. taxpayers. So being stewards of the data. So we also have some policies that we have to follow. So this is the levels of service policy. It's a ESDS, so that's Earth Science Data Systems policy. And you can see that there's several different basic, standard, and comprehensive levels of service that we want to follow. So the the basic level of service might get things like, here's raw data and here's calibrated data, but it might not have the higher level sort of things that you get from standard data, where you're wanting to actually have swath data and then gridded data and then eventually near real-time data. And having that accessible in different ways and different products and different sorts of services is what we try to do. So you can see here on the right, browse imagery, Subsetting and reformatting are really more sort of standard levels of service. Reprojection, resampling are the more comprehensive levels of service. These levels of service are usually set at the project level, and they're set sort of early on in the project. But there are always exceptions for different collections within a project. All right, so I'm going to shift gears a little bit now and tell you who we are, and then I'll get into what we are in a minute. All right, so you've heard us call this the transformation train. And some of you are intimately familiar with what a train is, but I'll give you a little bit of a background of what a train is for everyone else. So NASA Earth Data uses something called the Scaled Agile Framework. You've probably heard of Agile. It's a way of doing generally software development, but it can be used for other things too. And that works really well on a small number of people and a small number of teams. And as you get bigger and bigger to more enterprise level things, it gets harder and harder. So we have found something called Scaled Agile Framework, and it does a pretty good job of letting us work together while working separately on things, but not be in silos. So the idea is that we have different trains that do different work, but they're able to talk to each other cross-train. And each train has a certain number of teams, generally 10 to 15 teams on it. So the 4 trains that NASA Earth Data has is the ingest and archive train, which gets data into the archive. There's the platform train, which is really the bottom that everything sits on. That's basically the AWS infrastructure and the services that go around that. There's search and discovery, which some of you have probably been in some meetings, some sessions this week talking about Earth Data search and other things for discovering and finding data. And then there's the transformation train. And we get to be Thomas because it's alphabetical, and also we start with a T. So we'll just go with that. So the transformation train is the train that I'm talking about. It's the train that I am on. And then I'll tell you a little bit about the train, right? So who is the transformation train? So we have a triad at the top. There's the product manager, me, the architect, Owen, who you just met, and Heather Grams, who's our engineer. She's not here today, but that's okay. She does a lot of good work. So we have 14 teams. Let me do this math real quick. There's 15 on this list. So this is a 15-team train, and you can follow more information there on the link if you want to Earth Data Wiki if you're interested in finding out more. But we've got sort of 2 kinds of cars on the train. We don't call them cars. I made the cars thing up for this particular presentation. But there's the box cars, or the services that actually do the work, that carry the load. Those are things like Harmony, OpenDAP, the data services team, Earth Data GIS, EGIS, Gibbs, Cloud Giovanni, and Open Altimetry. They all have services that they provide, data transformations. You'll hear a little bit about those here in a few minutes. We got some good talks to talk through some of those. And then there's also DACs that are trying to get data into the service, into services. So I will define a DAC. So a DAC is a distributed active archive center. So a DAC is a domain-specific data archive that is looking at and talking to the community for a specific domain, science domain. And those teams that we have on our train are GESDISC, LPDAC, LADSDAC, ASF, ASDC, OBDAC, and PODAC. Other DACs actually get their data into services on the train, but they aren't fully involved as a team because they usually have more one-off or smaller requests. All right, so what transformation services are there? I will spin over, I'll go over the slide really quickly just to give you an idea that we have programmatic and web access services. You'll hear about a few of those later. There's Harmony services. So within Harmony itself, there's several different types of services. NetCDF to ZAR, there's a level 2 subsetter, trajectory subsetter. There's a bunch of different services that fit within Harmony itself. There are imagery and raster analysis services. I talked about Earth Data GIS. Worldview and Gibbs are 2 other ones. Hang on just a second. And then we have some web applications, some Worldview, Giovanni, Open Altimetry, and Appears. You'll notice that some of these kind of cross across what they do. So not just web applications, but also APIs. All right, so here's our vision as a transformation train. We are trying to provide equitable services. We understand that not everyone has the same experience and background. We want to be consistent in the services that we're providing. We want to be compatible, maybe interoperable is a good word there, with typical workflows and community technologies. We want to be lean or agile in the way we do this. We want to actually be able to do this in a cost-effective way and use all of the services that are available to us through the platform tree. And we want to be deliberate. So we want to actually focus on delivering the maximum value based on the expertise that we have across our enterprise. And we want to make decisions about, hey, should we develop something new within the train, or should we find a third-party tool that we do something with? All right, and where are we going as a train? So right now we're sort of in the process of streamlining our overall service offerings. If you're around NASA Earth Data, you may have heard convergence as the word. That's kind of what we're talking about there is making our offerings a little more converged and fewer. We want to streamline the onboarding process, make it easier for DACs and data providers to get into services. And we want to make better documentation that's more findable. We want to continue our engagement with open source communities outside of NASA, kind of through things like ESIP. Owen will talk about some work that he's been doing outside in the open source community. And then we also want to improve support of cloud optimized data sets and workflows to provide analysis in place so that scientists can come to the data and do analysis. I think, yep, that's all I had. So if you have any questions, I'd be glad to take those now or in chat, either way.
Are there any questions in the room?
You didn't mention Ingest Archive on his little train thing.
He did. It was Toby and James.
And he didn't draw attention to the fact the platform was over the platform.
I don't know if you can hear this, Dane, but Doug's dissecting your joke.
Yes.
Platform.
It's just a label, Doug. It's not, there's nothing. No, you're right. I did actually put it on the platform. Just
All right. Are there any questions in the room? Are there any questions online? Okay, you got off lightly there, Dane. James, I think you're up next.
All right, thanks.
Thank you, Owen. Let me share my screen. Okay. Good afternoon. As Owen said, I'm James Norton, and I'm a contractor on NASA's EED3 program and one of the core Harmony developers. I'm going to give you a high-level overview of Harmony, but first let's define some terms that I'll be using. These definitions may be Harmony specific. Other similar projects may use other terms for the same things, but this is what Harmony uses. First, a provider is someone or some group that makes data or services available through Harmony. The Common Metadata Repository is probably familiar to all of you, but if not, it's the NASA system that catalogs Earth science data. It uses a unified metadata model, or UMM. Of the various models, Harmony is generally concerned with collections, granules, variables, and services, particularly transformation services. Containers are software applications packaged up with everything needed to run them. Harmony uses Kubernetes, which is a container orchestration system used to build applications out of multiple containers. A node is a single compute instance, which may be a physical machine or a virtual machine, and nodes are used to build up a Kubernetes cluster. A pod is the smallest deployable unit of work or compute in Kubernetes. Each pod consists of one or more containers. The containers in a pod work together to provide a service, and they can share resources like a mounted file system or an exposed port. A deployment is a Kubernetes system that manages a group of identical pods to make sure that the number of running pods stays a fixed number. So if pods get sick or die off, it'll start up new ones. Stack is the spatial temporal access catalog, which basically is an extension of GeoJSON that can be used to describe data and specify its location. A job in Harmony is all the work done on behalf of a single request, And finally, we have work items, which are the fundamental unit of work for Harmony. Jobs may consist of many work items, typically one per granule per service. So what is Harmony? Well, before we get to that, we might want to first ask, why is Harmony? Consider a data provider. They have all this great data that they make available to their users. Now, the users want the data transformed in some way, say reformatted. So they add a service to do this. And of course, they want to make their data and services available to all their users, so they create a web API to provide access. And then the users want even more transformations, say spatial subsetting. So they add more services. And they need to worry about things like authenticating their users and all the other issues that go with managing web applications. And of course, everyone is migrating to the cloud these days, so they probably have to deal with all of that as well. And this is happening across all providers. They all have to solve the same problems. And consider the users. How can they find the data they want and transform it in the ways they need without wrangling APIs from different providers? Which brings us back to, what is Harmony? Harmony manages and runs services on behalf of providers. It provides a unified API for users and removes the burden of running services from providers. Providers can focus on building their services in a common way using a Harmony provided service library written in Python. This library handles common chores like downloading data, staging results, and generating stack catalogs. Harmony automatically scales on demand. As more users make requests or requests scale in size, Harmony will spin up new instances of service pods to meet demand. Harmony can handle the user requests with millions of granules and thousands of variables. Harmony also employs a fair queuing strategy to prevent individual users from hogging all the compute resources. This means that if a user spins up a big job, which is fine, as new users come in, their jobs will have equal access to the running services, so they don't get crowded out by the older job. So users are happy. Harmony currently supports 12 core services from about half a dozen providers. And if I'm missing any providers, I apologize. These services can be used individually or chained together, including chaining of services from different providers. All services and service chains are vetted by data providers to verify that they work with their data. Not every service can be used with every data from every provider. So what transformations do these services provide? They provide subsetting, including spatial, temporal, variable, and dimension subsetting. They provide reformatting, such as transforming a netcdf file into a ZAR file. They provide reprojection. They provide aggregation, such as concatenating data files together, like playing cards on a deck, as well as extending files, which is similar to concatenation, but it's like it stitches the files together like a quilt. So how does it work? Harmony consists of two major components. The first component is a front end that provides APIs based on several OGC APIs, coverages, environment data retrieval, and web map service. This component also manages the job for user requests. It implements a core application that runs behind a load balancer and a set of microservices running in a Kubernetes cluster. The second component is the backend, which runs the transformation services needed for each job. It is run in the same Kubernetes cluster as the front-end microservices and consists of groups of pods, one group for each core service, with each pod performing work for the service. So let's go through a typical workflow. When a user request comes in, Harmony creates a new job to fulfill the request. If the request is synchronous, Harmony will hold the connection open until the job is done. If the request is asynchronous, Harmony will redirect the user to a job status page. Harmony first determines which services to use based on the requested collection, variables, and transformations. Then for each service, it stores information about the service and operation, and this is called a step. Then Harmony creates one or more pieces of work for the first step. These pieces of work are called work items. Harmony then writes out the job, steps, and work items for the first step to the database. While this is happening, the microservices are communicating with the core application via queues while also interacting with the database. Meanwhile, on the back end, the service pods are constantly polling the front end for work. When a pod asks the front end for work, Harmony retrieves a work item for the service and returns it. This is happening in parallel across all the service pods. When a service pod finishes its work, it sends a response to the front end. Then the front end creates one or more new work items for the next step and updates the database using one of the microservices. This process continues until all the work items for all the steps in a job are complete. For synchronous requests, when all the work for a job is complete, Harmony reads the results from the database and sends a response to the user. For asynchronous requests, Harmony updates the job status page as each work item update comes in for the services. The job status page will eventually contain links to the final output stack catalog. So now you know how things work at a high level. Let's zoom into a service pod to see what's happening at the low level. The service pods each have two containers, the manager and the worker. When the pod is not currently performing work, the manager uses a long polling HTTP request to the Harmony front end to request work for the specific transformation service. When the manager receives a work item from Harmony, it invokes the service container using a Kubernetes exec call. This runs the service code inside the worker container. The service code writes out the transformed data along with a stack catalog pointing to it to an S3 bucket. The manager then sends an update to Harmony containing the status of the work, failed or successful, and the location of the stack catalog. The use of stack catalogs is the key to being able to chain services together. So let's take a look at how that works using example service chain. The first service that most service chains use is the query CMAR service. This service searches for granules in the CMR using a query based on the user request. Query CMAR then generates a set of stack catalogs, one for each granule it found. These catalogs become the inputs to the work items in the next step, in this case, a level 2 subsetter. Each instance of the L2 subsetter then generates the transform granule and a stack catalog based on its results. Services can also consume multiple outputs from the previous step. Here we have the concise aggregation service consuming the output from the multiple granules run through L2SS. Finally, concise generates its data in a single stack catalog. So how does it scale? If we go back to our architecture diagram, we can see below, we can see how it scales. For the Harmony core services and microservices, we have a fixed number running of instances with no auto scaling, so they don't scale. But for the database, we use Amazon Aurora Serverless DB to handle the scaling automatically. And for Kubernetes, we scale our Kubernetes resources at 2 levels. Our cluster starts out running on a fixed minimum number of nodes. And we utilize a Kubernetes service called Cluster Autoscaler that monitors nodes metrics like memory and CPU usage. It automatically spins up new nodes and merges them into the cluster as demand rises. And it will continue doing this process up to a configurable limit of nodes. As demand decreases, the autoscaler will automatically destroy unneeded nodes. And as nodes are added or removed from the cluster, Kubernetes automatically redistributes the running pods for us. Harmony also automatically scales the number of pods running for each transformation service. Each set of pods for a service is managed by a Kubernetes deployment, shown here by the yellow, blue, and lavender boxes. The deployments are responsible for maintaining a fixed number of running pods for the service groups. If a pod fails a health check, then the deployment will terminate it and start a new pod. The deployment will continue to start new pods until the required number is met. So the deployment will make sure we have a fixed number of pods running, but we want to scale that with load. And if we want to scale that with load, we have to use another service called the Horizontal Pod Autoscaler, or HPA. This service uses a configurable set of metrics to tell a deployment how many pods it should keep running. And these metrics are gathered from the pods themselves and from the Harmony front end by another service running in Kubernetes called Prometheus. The HPAs pull metrics from Prometheus and tell the deployment how many pods to keep running. In our case, we use a metric based on the number of available work items for a service and the existing number of running pods. And so as our load goes up, if we get more work items and they're not being processed, the HPA tells the deployment to add more pods. And as it works off those work items, as they get processed off, it will tell the deployment to scale back the pods if they're not needed anymore. And you might be wondering, do we lose work being done by a pod that gets scaled down? And the answer is no, because our pods are configured with a safeguard to prevent the deployment from terminating them before they complete a running work item. So once they complete the running work item, then the deployment can go ahead and terminate them. So that's Harmony in Whirlwind, and what it does and why it does it. So please, if you are interested in doing data science with NASA, Earth data science, follow this link and check out Harmony. And if you have questions, I have, looks like I have about 2 or 3 minutes.
Are there any questions in the room? So James, I have a question. So if someone wants to use a Harmony service, like, are there a couple of ways that you could sort of quickly talk through for someone to sort of get their hands dirty with using, you know, I know Samba, like Danny's about to talk about, or
Sure. I didn't include it on here, and I probably should have. But the easiest way to do it is to go through the Earth Data Search. If you go through Earth Data Search, you could access Harmony services and pull your granular step process down that way. That's definitely the easiest way to do it. There's also you can use straight curl commands if you want. If you go to this link, it has documentation. It has a sample notebook that you can actually run in GitHub Colab, or sorry, is that GitHub? Or sorry, that's Google Colab. And so it's interactive. There's also online documentation that you can check out that tells you exactly how to use curl or to use Python to access this. We also provide a library called Harmony Pi, which I think is on PyPy, and you can pull that down, and that will make it even easier for you to interact with Harmony and to do data science through Harmony.
Great, thanks. Any questions still out there? And any online that I haven't spotted?
Yeah, and sorry I didn't have my camera on earlier. My computer is situated such that you would have just seen the side of my head, and I didn't think that was probably that great.
No worries. All right, if there aren't any questions, thanks again, James.
Sure.
Next up, we have Danny Kaplan.
Is this going to be sharing everything?
You have to share. It's not
sharing. Share. It's not sharing. On multiple sharing.
Please.
Let's see if this works. Seems like it might have worked. All right. Yeah. So. Hello, everyone, and appreciate the opportunity to share some of our work with you all. My name is Danny Kaufman. I'm from the Atmospheric Sciences Data Center, and this work is a collaboration between a lot of folks, people listed on the slide, which include folks at ASDC, the Atmospheric Science Data Center, as well as ESDIS and even the other data centers as well, to figure out how to do these kinds of service chains that James just talked about. So in this case, I'm going to introduce you to the service chain that we put together for the TEMPO mission, which is an air quality mission. And let's see, I'm going to start off, just give you a very, very quick primer on what TEMPO is, talk about some of the tools that we already had in hand, including Harmony, and some of the challenges that we were trying to address with this, and ultimately with the service chain that we ended up with. So TEMPO is the Tropospheric Emissions Monitoring of Pollution instrument. It was launched last year, and it was actually selected as NASA's first Earth Venture class instrument in 2012, which is like a program for lower cost, competitive, science-driven instruments. It measures atmospheric composition, and you can see it on the slide. It's that silver box. It's lower cost, partly because it's put on top of a communication satellite, which is the big like bus-sized thing there. TEMPO measures atmospheric composition over North America every hour during daylight hours. It's in geostationary orbit, so it provides this continuous coverage, which is a real boon for studying air pollution over the US. It's part of a broader constellation of geostationary satellites, one that's already launched, one that will launch in a couple of years over Europe. TEMPO measures things like ozone, nitrogen dioxide, formaldehyde, so it can look at pollution from traffic and from urban centers and things like that. The resolution is suburban scale, 2 by 5 kilometers squared, roughly at its center. And yeah, so because we have this awesome data set and we want to enable and empower folks to do all the kinds of analysis that they want, you could just think of some real basic analyses like time series. Often when you want to do time series analysis or other types of exploratory data analysis, you want to look at the data from a particular location and look at it through a long period of time. And so in a lot of cases, this means taking the data, spatially subsetting it, and then possibly either concatenating it in memory or doing it in the cloud and treating it like a virtual aggregation. In this case, we are trying to provide users with the ability to do this use case where they want to download multiple files in order to analyze it themselves, but not have to do the subsetting and the concatenation themselves. That can be done on the cloud in Harmony. So a little bit about how the data are structured for Tempo is trying to give you an illustration of that here. So this is a view of the data coming from Tempo, seeing the hourly scans. But within those hourly scans, you can see, and I don't know if it might be a little bit hard to see, but there are vertical lines that are roughly vertical, curved north to south, that those delineate the actual files as they're generated by the instrument processing, and that's to make it more efficient for network transfer and things. So each one of those represents a 6-minute slice. So there's roughly 9 or 10 granules that are created, and each one of those is a separate file. So schematically, those files are, the data within those files is organized like this, where most of the variables are 2-dimensional variables. So you can see like 3 granules here, a yellow, pink, and green, and they have a east-west dimension that is called mirror step because it reflects the instrument's mirror, and then a cross-track dimension, so opposite to the direction that the instrument is moving. And time is increasing from right to left or east to west. So as it scans, kind of just showing this again, we get like 1 scan and we have all of the granules from that scan. Then it restarts again and it scans east to west once more. We get the granules for that scan and so on and so forth. So you end up with all of these scans. And to do this subsetting and concatenation, what we ultimately want to be able to provide the users was concatenated files that were concatenated within each of those scans. So all of the granules for scan 1, 2, and 3, after subsetting, to be stitched together, like James described as a quilt, stitch those together. And then we want to concatenate across those scans. So that was his analogy, which I really like, James, the playing cards being stacked on top of each other. The tools that we already had at hand. So Harmony, just as James described, this awesome process orchestration system. Concise is another service that was developed by the Physical Oceanography Data Center that does the type of concatenation that is the playing cards stacked on top of each other. We have the level 2 subsetter and then other open source libraries. So here's my graphic. That actually, it's not my graphic, but it was the graphic that someone else shared with me, and using it here to illustrate kind of another view of Harmony. So Harmony being this API, part of Harmony being the API to enable different kinds of applications to make the requests to Harmony, and then Harmony is providing a common message to various services. And so on. So the different services, that can be the concise, the subsetter, and so on. And we want to be able to chain them together just to be able to do subsetting and multiple types of concatenation. So another illustration illustrating this stacking of the playing cards in the case of tempo, which would be where different files would be stacked on top of each other, and you would end up with something that's schematically shown here, where you have a new stack dimension. This is not originally a dimension in the files, but is added on at the end of the once Concise operates on them. So some of the challenges, these aren't like really wild challenges. These are pretty common sense challenges. I don't know, but they were things that we needed to keep in mind and had to deal with that other people are also tackling in other ways as well. So we wanted to create this new process for concatenation without reinventing the wheel, as many of us are trying to do, not reinvent the wheel over and over again. We needed to be able to handle a grouped structure within the data files. These are netcdf4 files, and they have this group structure where this is just a schematic showing that where variables can exist within different groups in a hierarchy within the files, and not all of the tooling for netcdf4 files is able to handle that elegantly yet. And I think Owen's going to be talking about efforts to make that more elegant handling of that just after this talk. And then just the process of hooking it up into Harmony is not trivial. Harmony is awesome, but there's quite a number of kind of configuration things and like this passing of the stack catalogs that needs to be kind of learned as you build a new service into the system. Okay, so I already showed Concise and this way to stack the stack files upon each other that was already there, and this was the new type of concatenation that we wanted to add into the Harmony service ecosystem, was this stitching together. We decided to call it Stitchy just because that's fun to say, and we have a little bumblebee that does it. So the result of this would be this quilt, basically, again. So the granules, once they're stacked together, we don't have a new dimension. It's stitched together along the existing mirror step. So the result is an operation that looks like this, where the different granules are stitched together along that mirror step dimension, and that creates an intermediate object from the Stitchy service. And then that goes for every scan within that Tempo is generating. So each of these would be different instances of the services. And then after all of those Stitchy operations are done, then it's passed to Concise, and the resulting files are concatenated together along a new dimension. So Stitchy, the new service that was added, the inputs and outputs are very simple. It's basically takes a list of files, and it takes a dimension name, so that way it knows which dimension to concatenates along it, and puts an output. And the inputs and outputs are simple because we want to make this ultimately generalizable, so that way it's not just Tempo that's using this. The Harmony service ecosystem is geared for being able to reuse these services for many missions within the NASA Earth data. A little bit more detail on what's happening here. There's several steps. After the inputs are validated, then the operations to flatten all of the groups within the file. Again, this is what we're trying to avoid with some of the development in data tree. But as things stand now, we needed to get this to deliver services for the Tempo users now. So we took this approach to flatten all of the groups, open it as an Xarray data set, use the existing tooling, again, not reinventing the wheel. Xarray concat is a very powerful function. And at the end of that, we reconstruct the groups and pass that back. There's a whole bunch of steps within each of those steps to actually make it all work. And all of that is called Stitchy. Yeah, so once these messages are passed to Harmony, and if somebody requests something that includes subsetting by space, by time, or variables, as well as requests to concatenate the resulting file, we end up with a chain that looks like this, where the request comes in, just like James showed, like most services, we start with querying of the metadata. Instances of the subsetter are run for each of the granules. This is passed to another very, very simple service that we created just to do grouping of figuring out which granules belong to which scan. Those are passed to Stitchy. The results of Stitchy are passed to Concise, and the output gets passed back to the user. And actually, we have an animation that one of our folks on the team put together that shows this in a much cooler way. So we have Batchy the bat, taking all of the, this is after the subsetter has operated on them and takes all of the granules, and Batchy puts them into batches for each scan of the tempo instrument, each time that tempo went from east to west. Then we have Stitchy, and Stitchy takes all of the granules for all of the granules within each scan and does that concatenation along the mirror step dimension. So that way we end up with a single file for each scan. That's what's shown here. Then each of those intermediate files would then be passed to an instance of Concise. Concise will create a new dimension within the file, stack those together to create an output netcdf file that would be delivered to the user. And whoops, didn't mean to exit it. Okay, yeah, and all of that is then put on the back end as it's configured as a service chain that we were calling it Samba. That is this. I'm not even sure if I remember the acronym now. Subsetting and multi-dimensional batching and aggregation in Harmony. So that's run just when a user requests subsetting and concatenation for tempo data. So in summary, tempo really provides an unprecedented view of air quality. It is showing us parts of our atmospheric composition that we've never seen before in the resolution. Harmony just does an incredible job of managing the operational running of these services, handling requests, and this new service, actually it's two new services, Stitchy and Batchy, that we developed and integrated into Harmony to do a chain of subsetting and concatenating again. And this is all invoked when somebody requests these things, either through Earth Data Search or Harmony Pi or another means. And that's all I have. Thanks. And I'm happy to answer any questions. Yeah.
All right, so this is all right.
I'll try to repeat it. I'll repeat it.
Okay, so first of all, I really like the animation.
Yes. Everybody,
Love that.
Andre Kim, he created that. It's amazing. Yeah.
Yeah. No, if we could get more animations to kind of summarize what we're doing, like a nutshell, that would be awesome. Great job. But the question is, how long did it take to run that from end to end, chaining all those services together? Do you have an idea how long that took?
Like to run it when somebody requests things, like
right, all those different chains. Like, say for instance, that animation, that was a series of services that was, that happened one after each other. How long did that take in general to do it real time?
It totally depends on how many, how much data is being requested. I mean, I've run instances where it's taken, I want to say, a couple minutes is is often the case. Yeah, I think that's the order of magnitude generally. Yeah.
Thank you.
Yeah.
I'll take
Yeah, other questions? All right, yeah. Yeah, and I'll just say that the work that Owen is going to present next is stuff that we're really interested in, because some of this stuff that's happening in Stitchy and Batchy will also hopefully be able to be done for users in the cloud using things like DataTree. Yeah.
All right. Okay, so as ever, I'm the one that's furthest in the weeds with things. I'm Owen Littlejohns. I'm the architect on the transformation train on NASA EED. Sort of Dane gave a great overview of some of the things that we do. I've been involved with some of the other Harmony backend services as well. But today I want to talk about some work that we've done with the Xarray team to try and work with the open source community to get something that we really care about to be available for our own usage for things like Samba. But then also for the wider community. And specifically, that's trying to make sure Xarray can handle hierarchical data files. I have perhaps two things I want people to take away from this talk. I'm just going to say them up front. Firstly, I want people to care about the ability to use Xarray with hierarchical files. That's kind of obvious. But also, like, I want to sort of maybe push this emphasis on let's work with the open source community. This is maybe one of the first times that as a train, we've engaged in this way. And I think even though we're not across the finish line yet, it's gone really well. And I would love to see this happening more. So maybe I'm sort of concluding at the very beginning, but like, it's something that I care about. And I think that it's something that we should try and do more of. You know, as I say on this slide, right? We have some really smart folks who work, whether it's on EED, whether it's at the DAX, and they have a whole heap of expertise, but we don't have to write all the code and we don't have to maintain it all. We don't have to, you know, put it in a GitHub repo that no one else can ever access. Like, let's engage with some of these things, like the sort of communities like Pangeo. Let's solve the problem once instead of having, I don't know, 3 different DACs who write a solution to something that they don't each know about. And so we've actually solved it 3 times. Like, let's do it once. Let's make it available to everybody. Let's just sort of embrace that open source sort of community. Specifically talking about Xarray, I think most people in the room know what Xarray is, but for those of you who don't, it's a Python package. It's great at opening up your data files, like think NetCDF4, HDF5, even ZAR. You know, you can crack those files open. You can look at what's in there. You can interact with them. Like Danny showed in his talk, there's a concat command, which allows you to do interesting things with different data sets. So the specific problem that we were trying to solve, and it's one that's been around for a long time. So if we look at some data over here on this slide, this is something open in Panoply on the left. This is a sea surface temperature product from the PODAC. You can see it's really nice, right? Like there's maybe what, I can't count from here, but like 8 or 9 variables. They're all in the root group of the NetCDF4 file. And, you know, they're really easy to find. And then with Xarray on the right there, and it wouldn't be something I'm presenting without Jupyter Notebook, like you can just open up Xarray, you can use the open data set function within Xarray and, you know, just display that data and Xarray can cope with it, right? You can see there's the same variables present and Xarray does some of its clever things to say, okay, here are the coordinate variables. These are the things that link to those coordinate variables. You know, it's doing a lot of fun, good stuff that's really helpful. But not all data are flat. And in fact, we've seen some examples of, this is ISAT2, I think it's ATL08, which is a land and vegetation type product. We've seen, I think, ATL03 a couple of times already in the last few days with Luis Lopez talk this morning. And I think Andy Barrett's talked about ISAT2 as well. It's a complicated beast. There's, I think, 6 beams that ISAT has. And so the structure of the files is complicated. There are like 6 really big groups within this HDF5 file. Each of those groups, you know, represents a beam. The groups have subgroups. They also have variables. Some of those subgroups have subgroups. They also might have variables, and it goes on, and it's just this big mess. And Xarray can't read the whole thing at once, which is a pain. You know, you can't do some of these really cool things that Xarray can do with that file. And so that's the problem we want to solve. We want to make it so that you can open that in Xarray and you can do all the Xarray good stuff. And it's something that it's not just that we want for our, our own internal programming, like, Danny was talking about, other people want this, end users want this. So it's a win for everyone. The really good news is we don't have to write the code because someone already has. So Tom Nicholas, who again has been mentioned over the last few days more for Virtualize-R, he also has the Xarray data tree Python package that has existed out there since March 2022. It's kind of like a bit of a prototype effort that he put together that extends the Xarray data model. So, for those of you who use Xarray, there is the data set. The data set is approximately a group in the netcdf4 files. He wrote this thing that is essentially a tree representation of those hierarchical files. So each group in a netcdf4 file is a node on that tree. The nodes sort of know their parents, they know their children, they have all the same sort of good capabilities that a data set does. So that means that you can extend what already exists in Xarray to do operations across the whole of that tree. So you can do, like, if you wanted to concatenate things together, you can concatenate the same variables in the same groups in 2 files, even though it's got all this complicated hierarchy. So it's, really, really powerful stuff. So I just wanted to show a couple of examples of what this actually looks like. It's still tiny bit left to go, but this is me using it sort of locally. This is the same ATL08 file that I showed in Panoply a couple of slides ago with all of that complicated structure. It's not the whole thing because there's an awful lot of stuff in there. But if you look at this and you're familiar with Xarray, at the bottom, this stuff looks familiar, right? Like you can see the variables. You can see that it's separated out the coordinate, the delta time variable, and it tells you, hey, these things use delta time. That stuff not changed. But if you look higher up on that output, you can see it's got these groups and sort of nested groups. So you've got LAN segments, you've got, where is it? Signal photons. And then within LAN segments, there are 2 groups that I've minimized because I just can't fit it all on the same page. But yeah, we now have this structure, like with one call, that xr.openDataTree, xarray.openDataTree, it's past the whole file. And maybe sort of a brief tangent. Back when we were first migrating this code, like it took maybe 2 minutes, I think it was 2-3 minutes to open this file because it was doing something in a non-optimal way. While we were doing this, somebody who is completely not related with NASA in any way, someone who's not part of the Xarray core team, they saw what we were doing, they were following the GitHub issues, and they're like, oh yeah, I can fix that. And they submitted a PR, got it sorted. That opens in like 2 seconds now. And that's like 700 variables or something. And before it was taking 3 minutes. So we're already getting benefit from engaging with the open source community because they've made it so that this thing can actually be shown in my demo. But no, it's a massive win. And that's exactly the sort of thing that we want to be getting out of this sort of engagement. I'm not going to go into too many details on how to like play around with these things, but I did want to show that you can do operations across, multiple parts of the tree. So on the left here, I've got an example just setting up a simple tree. It's got a single parent node, Homer Simpson, and then like there are 3 children there, Bart, Lisa, and Maggie. They've all got ages. And so you can see on the left like how it represents it. You can see Homer's 39, Lisa's 8, all of that good stuff. On the right is where you start to use that. I think my face is in the way, but on the very right-hand side there's a filtering that's going on where we're just trying to find all of the people on that tree that are adults. So we're filtering for everyone that has an age greater than 18. And you can see that the output there is just Homer because Homer's the only adult out of the 4 of them. Other things you can do, there's sort of mathematical things you can do to all the nodes on the tree. The other example showing just adding 10 to all of the variables. And so like it's a one-liner, and then you've just got every single variable on all the nodes there, their value have been increased by 10. So now Homer's 49. Really simple stuff, not very like special and earth science related, but it does show kind of the power that you get from this data tree structure and how it can just, do things across the whole tree. So switching gears a little bit to maybe talk about sort of the nature of this collaboration. There have been quite a few people involved. I've already mentioned Tom Nicholas at Xarray. There are other Xarray folks like Stefan Hoyer and Eustace. They've been really, really helpful in helping us get set up and, really making sure we know what we're doing, basically. obviously I'm involved. I'm on EED3, Matt Savoy from NSIDC and Eni Awawale from the JESDISC. We've all been trying to help out here. The goal, I mean, the obvious goal is we want this thing in Xarray. We want it released. We want to just be able to do from Xarray open data tree. You know, that's what we want. We want people to be able to access their files and just do it easily on one line. But it's not just a case of, hey, I'm going to copy this file from this repo into that repo. You know, we want to make sure that we're understanding it so that it's not just essentially 1.5 people that know the code. And there's quite a lot of code in there, you know, because in the future, there are going to be issues. Like, it's code. There's going to be something that's not quite right, or maybe there's a new feature someone wants. And so we want it to be in the future that there's a bunch of us that can help out and, you know, reduce that. I don't know if people prefer bus factor, lottery factor, but we want to be reducing that so that, you know, if Tom does win the lottery, you know, we can still use this code and improve it. And also, you know, it's a good opportunity now. Like, the code is sat in this separate repo for a while. It's about 2 years old now. And while we're doing that migration, if we're really thoroughly looking at it, we can maybe be making optimizations like Alfonso's PR that I mentioned before. You know, we're able to find a way to make it better. And now it's running like 2 orders of magnitude quicker. So, you know, we want to be improving as we go as well. I'm getting to the end of my slides. So the lessons that we have learned, one of the big areas is communication. And a lot of this is obvious, you know, like, communication is important when dealing with software, and particularly when dealing with multiple teams, but it's even more so when they're not all in the same organization, right? Like, I work on the EED contract. We have our PI planning. We have our 2-week sprints. We're very sort of process oriented, and, you know, we have to deliver our objectives and all that good stuff. The Xarray folks work a bit differently, you know, and so making sure we talk well and we sort of marry up those 2 processes well is important. And I really do want to be fair to the Xarray folks. They did, I think, everything they can to make sure that we were set up for success. So the Xarray team has a fortnightly developer tag up. They've scheduled now like a weekly separate one because I think we were basically taking up all their time. But now we talk every week about getting this concluded. And so it's a really good chance for us to make sure we know where all the PRs are, you know, all the issues that are open relating to this. We do sort of use a lot of the GitHub functions, like, you know, like I said, PRs, issues, all of that good stuff, so that we can track it in a very open way and we all just know what's going on. But the last bit sort of that I do want to point out is, like, you do have to make sure you're having honest conversations about the scope of these things, you know, because I think there are a couple of conflicting priorities here. Like, we want to get this done as quickly as possible. We want it to be out there. We want to be using it. But also it needs to be really good, because Xarray is this massive, like, community used package, and it needs to be good, you know. So we need to make sure that we're not pushing things too early and releasing something that is too experimental, you know. And we're lucky in this case in that, you know, there's a couple of years of it being out there in its own separate thing, but it's still a little different to be in actually Xarray, because I don't think that a lot of people even knew this other package existed. So, like, we're going to get so many more users now that it's in Xarray proper. So yeah, just making sure that there's this clear understanding of not just what the big picture is, but what the steps along the way are, and just being honest in those conversations, I think, is pretty important. Other lessons that aren't necessarily communication. So I've already talked a little bit about this, about sort of reducing the lottery factor. You know, we're not planning to just help move the code over and then step away, because that's kind of rubbish to do. We're helping going forward as well. So in fact, the 3 of us that I mentioned, Matt, Eni, and myself, we're now actually Xarray core contributors, and, you know, we should be helping as we go forward. If people are opening issues in GitHub against this code that we now are invested in and have signed off on, we should be helping to make sure that it's up to snuff. I guess sort of my last slide is going to speak to this a little bit as well. Like, it's going to take a little bit longer than planned. These things often do, and it definitely did in this case. But it is also a really good opportunity for learning stuff. Like, Xarray do things a little bit differently to how, you know, the development teams I've worked with in EED do things. And so it's just a great chance to get out of your own echo chamber and, like, learn how to do things a little differently. And I think I picked up some really valuable things from that. And we've brought them back, in fact, to some of the things we do on the DAS team that I work on. And like I say, I sort of opened up a little bit with this. Like, we're not quite there yet, but I really do think that this has worked well. And I do think we should do more of this. Like, we don't need to own all of the code. Like, if we do own all the code, it often gets hidden away in repos not everyone has access to. Like, let's be engaging more with tools like Xarray. Like, there are lots of others out there that we use day to day in all sorts of our analyses. Like, every time we open up a Jupyter notebook and we're playing around with data, like, I feel like that's a place that we can be contributing rather than, like I say, I've got my repo in Bitbucket and no one else knows how to get to it. And it solves the problem really well, but I'm the only one that's ever going to use it. Like, that's not solving the problem. And yes, I've done that. So confession there. Speaking of confessions, last slide, I wrote this talk 6 weeks ago, and at that point I was convinced that you would be able to pip install Xarray and that you would be able to use the Open Data Tree function. At this point, you can't quite. Like, technically you can, it's hidden away in the guts of Xarray, and if you can find, like, through the right paths, you can import the Open Data Tree function, but it's not available at that, like, top level API, like, say, Open Dataset is. We're pretty close. There's a couple of PRs left to go, and we are actively working them. The hope is that it will come in the next main release of Xarray. They happen approximately once a month, sometimes a bit more if something fancy is going on, but it really is close. I will sort of actually be able to say it's there at some point when I'm presenting this. But yeah, it's coming soon. And it would be great if people could use it, test it out, file issues in GitHub if, you know, it's not working as you expect. Like, let's really kick the tires when it's, like, available, because yeah, I think this is pretty useful stuff. That's all I've got. Any questions? Patrick, you're either going to have to shout at me or because the microphone doesn't work.
It's okay. No, I just wanted to say this is really awesome. Like, I was there, we were as a station having the pattern of, well, Xarray doesn't support it. We're going to have to, like, build a lot of stuff on top of it or not use Xarray. And then seeing it be like, you know what, let's just give it back and make it work for us. And now we can use it. Good job.
Hey, I'll take it. Patrick was just being excited about this being a thing now.
What do you feel are the major barriers that prevent us from doing more of this type of collaboration with external open source communities?
That's a really good question. Like, my honest answer is that like, we weren't sure we were allowed to do it. Like, it was difficult with, like, contract language and stuff. Like, we didn't know that we could.
You can.
That's brilliant.
That could have gone really badly. This is great, exciting. Congratulations. Yes, I have a question. This is exciting. So I've been starting to contribute to PyDAP a little bit in the past couple of months. I think we interacted a little bit. So the way Xarray works, dataset, is that you can define engines to use as kind of like ways to open datasets and drivers kind of. And so PyDAP right now is one of them. PyDAP now supports groups. So is there going to be something like that where once it integrates, are the arguments going to be very similar as they are right now for open dataset, or is that going to be something?
Yeah, that's a really good question. So the way that the Open Data Tree function works is it's essentially calling those other, like, open dataset, like, engines. So I think there'd be a little bit of work to sort of have a, like, hey, if this is PyDAP, like, do this, but totally doable. You know, we've done it with, I think it's the NetCDF engine. I think the Zar one is the one that we've the two that we've looked at so far. But yeah, it should be a straightforward PR. Like, we should talk about that.
PyDAP then?
Yeah, awesome.
You briefly mentioned bringing best practices back to the DOS team from the Xarray folks.
Yeah.
Can you expound upon that a little bit?
Yeah, I mean, mostly it was looking at a lot of the stuff they're doing in their CI/CD pipelines, and, you know, they're a big fan of things like pre-commit and stuff. Probably getting a little in the weeds here, but, like, it was like taking some of those checks that they're doing and applying them to some of our Python packages, whether it's like MyPy, which I have spent so much time making things work with MyPy, it's untrue. But stuff like that, some of the other like linting checks and stuff, and just making sure that we can integrate them into our repos as well, because we were doing some of that stuff, but this seemed like a better way to do it.
Oh, that's why Eddie started talking about that.
Oh, yes.
Explains a lot. Thank you.
Yeah.
Is it possible to, I answer in 2 sentences max, how are these groups in data tree interpreted? In other words, does it only say I'm aware of these groups and you are here in the group hierarchy, or it actually has some specific understanding of what it has seen in the parent groups and then what's available in the child groups? Like when you say add 10 and then suddenly it magically knows to add 10 to everything in the children groups, it sounds like it's an advanced understanding of group hierarchy or some interpretation of group hierarchy. But again, only if it's easy in 2 sentences, otherwise, read the documentation.
So, I mean, I do want to touch on something there anyway. So each node is aware of its children. And so like, if you pick like, hey, I want to add 10 starting at this point, like it does everything below there by traversing the tree based on what it can find in that parent. But one of the things that sort of held up this work is sort of an idea of coordinate inheritance. And so when the trees are being instantiated, there's now this ability to make sure that firstly, the variables in the child nodes are consistent coordinate-wise with their parents. And also when you're sort of playing around with one of those child nodes, if you're sort of trying to ask, hey, what are the coordinates that are relevant to me? Like it knows about the coordinates higher up in the hierarchy. So that's more than 2 sentences and got a little off topic.
I appreciate it.
Yeah. Okay, well, thanks very much, guys. Next up, we have Kit.
Thanks a lot, Owen. I'd like to tell you that they saved the best for last, but don't get excited though. Maybe we'll come in for a soft landing here. So my name's Kit McManus. I'm the Assistant Systems Architect for the NASA Socioeconomic Data and Applications Center, or CDAC. For most of my career, I've been a GIS developer, and the name of my talk is Earth Data GIS is for GIS users. Can I just see a show of hands? How many people use GIS? Oh, a couple of us. I mean, would we call it using GIS when we display something in a Jupyter notebook? Maybe we're getting there. The GIS community, I think it's moving in that direction. But a lot of our NASA users, they do use desktop-based GIS, right? So there's this idea that we always struggle with when you're building tools. We have this field of dreams, right? Like if we build it, they will come. That hasn't been my experience. I've built a lot of tools, and if you do outreach, people come. If you stop doing outreach, then people don't come anymore. Anyone else have that experience? Yeah, I think that's commonplace. So the other approach is to go where the action is then, right? So if we look at these, user needs surveys, we see that there's enormous interest in GIS. What tools do people work with? 61% of users in 2022 worked with ArcGIS, 45% with QGIS. So a lot of our end users, they're GIS users, even if we kind of are, but maybe we stay away from the GUI and we just want to pull it in through Python like I do. So what do these users want to do? There could be some types of folks, they're emergency managers. They just need to display some data on the map. People can do a visual interpretation of it and get the latest information on a disaster that's coming into their area. Maybe there's another level where there's a GIS analyst who they don't just want to pull data into a map. They want to analyze it. They want to create their own cartographic products from it. Maybe they want to serve it out to other people over the web as well. We have, science PIs that we want to develop algorithms with GIS data. We want to do that at scale. We want to do it in the data lake if we can. Other scientists where we want to share science workflows with other people. We mentioned Jupyter Notebooks. I think we'll see in the user needs survey for this year that there's that area is growing a lot. And then we have some people that are, you know, hardcore developers, like I know many folks in this room are, that want to get under the hood, optimize how the GIS works. So Earth Data GIS supports all of these different use cases. It does it using some technology that, you know, isn't open source. Is there anyone from Esri in the room? I know that there are some open source Esri GitHubs. There's some open source stuff in Esri. This goes back to what Owen was saying, though. It's like, do we want to reinvent the wheel? Esri's doing a lot of good things, you know, even though it's proprietary. And, you know, I've spent maybe the first 10 years at CDAC working on open source GeoServer, GeoStack-based solutions, very near and dear to my heart. When I teach students, you know, I teach Intro to GIS to folks. I teach them ArcGIS, and you want to know why? Because there's a lot of documentation out there about it, because it does all things reasonably well. You know, in the open source community, and again, this is evolving, right? You get a lot of one-trick ponies, right? Like, or at least you used to. You get, you know, QGIS, and this, again, it's changed. It used to be that it only worked really well with vector data, and now it works well with all sorts of data. But I still use ArcGIS to teach new people, like to bring them in the door. And that's what we're doing here, is we're meeting people where they're at. They might not start out very sophisticated about how they're going to use, you know, geospatial information. They might not even understand what geospatial information really is, but we want them on the boat, right? We want to let them into the game. So if you've heard talks about EGIS, and I know many of you have, I recognize a lot of faces out there. You've heard a lot about these image services that we produce, you know, raster-based image services. One thing I want to emphasize that you might not have heard much before is that, you know, it's more than just visualization, these services. These are actually highly robust and functional services that support processing on the fly. I mean, if you're willing to go into the Esri camp and learn about raster function templates, all of a sudden you can do all sorts of analysis. Any geoprocessing tool in the library you can apply to this image server, and then on the fly get those results. So, you know, it's more expansive than visualization, although I think that, you know, one of the ways this technology leads, obviously, is in the visualization capabilities. If you want to check out some more of the image services on EGIS, at this point in the conference, I'm getting really tired of QR codes, man. But I put a lot of QR codes up myself. I don't know. My phone sometimes, like, I can't zoom in on it. It's like I got to turn my laptop around, but maybe we'll get a good user-friendly solution there too. Another thing that the EGIS team hasn't talked too much about up until now is feature services, right? So ArcGIS, you know, it supports a lot of vector data. There's a lot of powerful things that you can do with data that's served out in the vector formats. You know, we can stream those vectors to our GIS tools. You can download them, URS. You know, we need to think about how is this going to affect user registration. You know, is someone really, if they know what they're doing, unless we're locking things down immensely, they can get in there and download those features because they're being streamed to their desktop. You can query and chart attributes. You can do geoprocessing on the service and write the output wherever you want, an S3 bucket to your local drive, you know, whatever suits you. So I want to look at a specific case study of the Surface Water Ocean Topography Mission, or SWOT. You know, we've been working over the past few months with Nicholas Tarpinian at the Physical Oceanography DAC and Victoria McDonald. And we've been ingesting SWOT data on river reaches into EGIS. So what is SWOT? From my point of view, this is a game-changing data set for anyone doing hydrological analysis. You know, we're able in a 14-day period to have multiple measurements of the height, width, you know, the initial conditions in a river that you might see prior to a disaster event that could then inform you of like, how long is this flood going to take to drain out afterward. It's a view of the river reaches data set. I misspoke a second ago. It's a 21-day cycle, not a 14-day. But we see here it's being visualized by the water surface elevations, right? So in some cases, you see in the Rocky Mountains, obviously the mountains are at a higher elevation as well, but it's really the delta, right? Like over time, are we seeing the water surface elevation change in a river? So here's a look at SWOT and EGIS. If I'm lucky, the animation will start, okay? So you can see here, for each step in this animation, that 21-day cycle of, which river reaches are being captured per day. It's not as good as Danny's animation. That was an awesome animation. At the end of the day, a GIS user, they're used to ArcGIS or QGIS. They can pull this data in, they can chart it. So here in ArcGIS Pro, we're looking at, a specific river reach over time, and then you can see how the elevation of the water column has changed. So how did we get here? In order to play in the Esri ecosystem, you do have to meet certain requirements for data structure. And, it's on us at NASA to leverage them to open up those structures more and more. But as it is now, in order to have a feature service, you need to make a copy of feature data and put it in an enterprise geodatabase. So that required us to do a lot of back propagation. For SWOT, each day there's between 0.5 gig and 2 gigabytes of new data delivered. This product, it just went public in March of 2024, but the data was available actually from January. So we needed to update our feature layer to have all that data. So here's some details of, how we get the zip files from S3. This is another thing I'd love for our community to leverage Esri on. Esri has a cloud native structure for dealing with raster data sets, but they don't have that yet for dealing with vector data sets. So for a vector data set, we need to pull it and put it in an enterprise geodatabase. So we're using just basic Python functions to merge those data and build attribute tables. We do some post-processing in order to time enable the data set. What we found is that if you run this in steps of seven days of data at a time, there are some performance improvements there. If you went beyond seven days worth of data or 10 gigabytes, the processing really slowed down a lot. So a very simple procedure of taking shapefiles, merging them together, appending them into an enterprise geodatabase, doing a little bit of post-processing to handle the time enablement. So, here's a look of a 7-day period. We see that not a very interesting chart, but it has some good information in it. Merging the feature classes and then appending them into the enterprise geodatabase is really where the time comes in. So this algorithm, it takes about an hour actually to append, to do the back propagation per time step. However, for daily updates, it's pretty fast. Now that we have the whole catalog available each day when new data comes out, we're on a similar algorithm. You can complete in, 10 minutes. I don't know exactly how long, but much less time. So here's one more QR code for you, in case you want to see more of those feature services in action. And I just want to bring us back and I say, EGIS is for GIS users. One of the selling points I actually use for students, I say, you want a career in GIS? Some days you can just wear flip-flops. Like if you're digitizing something, you can drink a beer and digitize. They love it. I think I've got a lot of career GIS people that way. So, we need to keep in mind that although we're power users in this room, right? Like we're developers, the majority of people, they aren't. And that's what EGIS is for. It's for those GIS users who just want to get some spatial data and take a look at it, do some processing on it, hopefully. So thanks very much. I'll take any questions you have. Listen.
All right, kids. So you mentioned Earth data login, GIS. Sounds like it's a pain point. All right. Can you help me understand what's going on there?
So within this ecosystem, if you expose some feature data set, vector data set, by default, it's going to stream those features to someone's desktop GIS, right? So they're are they downloading the data? At that point, they can just say export and export it to a file on their local disk. So that's where the problem is.
Is Earth data login a part of that workflow now or no? I'm just curious. I'm not going to be honest.
Yeah, well, I mean, if you want to get into the EGIS system, right, then you need to do Earth data login as an entry point.
But does that prevent the streaming of data? Is it kind of a barrier once you're into the ecosystem?
Well, Justin, you're going to get my head cut off up here. The answer is a sophisticated user can get at the data, right?
Justin.
Uh-oh.
So they actually asked me that question. Does EDL need to get involved when we set up the Aegis? And I said, yeah, this is a data distribution. We need the metrics on it. So EDL is in that, just like it is with any of our other, you can think of this as a transformation service or something like that. Of course, we have notions of relaxed registration in other areas as well. So it's something we can look at again in the future. Or Vinny can look at it again in the future. I don't do this anymore, but I did when that decision was made.
It's my fault, is what I'm saying.
So the take-home message is EGIS. It's easy to use for folks. It's not just for visualization. That's my take-home message for all of us in here. It's not just a visualization surface.
So, do you have any metrics on this? Yes, we do.
In hand, not personally.
Right. No, we do. So, Aegis is servicing about 30% of the, I don't remember the number off the top of my head, but it's servicing around 30% of the requests that Harmony was at in terms of volume. So whatever Harmony's doing, Aegis, after only about a year, is already doing a third of that volume in terms of requests. So it's been really successful, and it's chipping into that 64% of users that didn't have a place before that. Why am I focusing this at Justin? He knows this already. It's shipping at that 64% of users that we didn't get to before. So from that perspective, this is a huge success for Resdis. So well done.
Thanks for the bailout, Doug.
I think that's all we've got. Thanks everyone for joining us. There were some questions on chat, but I think people were taking care of them. So thank you to the people who are answering those. And yeah, I think was the next thing at 6 p.m. There's a thing at New Belgium for Funding Friday. So just putting a plug out for that. But yeah, thanks again, everyone. Thanks for our speakers.